Hello everyone. So today is exactly the first video of our channel called How Does It Work, and we will be starting it with electrostatics, you know the first topic which we need to study in electromagnetism as a whole. So we won't be targeting any exam or something. We are going to just study it and for interest purposes. Okay. So I could have kept the background black, but to keep white is a purpose so that I can just make it a PDF and put it in the description box so you can download it. You need not to make any notes, or you may, and I suggest you should. So let's begin with electrostatics. So this is a subtopic which we are going to cover inside the whole of electromagnetism. First topic is electrostatics. So I guess you are good with that. Let's begin. You will be hearing these I'm sorry for that. You will be hearing these mouse clicks because I do not have I do not have a writing pad, you say, right? So I can't really just I can't really stop this sound. Okay, we have to write it from mouse. So let's begin. Okay, so what is the definition? Okay, so electrostatics, part of electromagnetism, is a branch of physics which deals with the study of charges and at rest. Okay, what does it mean? Statics. This static, being in a static position. Static position is exactly what you would think of when I say at rest. So electro means related to charge. Okay, charge, and this means rest. So the charge is at rest. So it doesn't necessarily means we are going to always keep the charge at rest. So the basic meaning of everything, the basis of everything is going to be from a charge at rest. All the formulas, all the expressions we are going to derive from a charge at rest. So I think you're good with that. We should begin without much explanation because these are very known terms. Okay, we should go and begin with the properties of charge, which almost everyone knows. Okay, everyone knows about what charge has as a property. Okay, now there are many properties of charge. The first and foremost and the most basic properties of charge is there are two types of charges, and I need not to tell anything about that. I think you know it already. Charge is of two types. One is positive, second one is negative, right? Okay, and I won't write this, you know that very well. Positive charges or negative charges, when I mean, if positive and positive are kept near each other, they will repel each other, and if the charge is opposite, they will attract each other. It is a very basic thing, so I need not to tell you. Charge in itself is a scalar quantity. Okay, it's a scalar quantity. Okay, doesn't have any direction, no vector law of addition, because it's, I can't really tell you why isn't it a vector. It's simply a scalar. So yeah, unit of charge, we need to understand. The unit of charge is coulomb. Okay, and one of the most surprising thing you will find is charge is not a fundamental quantity, right? Yes, a fundamental quantity which is used to derive the dimensions of charge is current and time. So we all know from our basic knowledge. If you don't, we will be covering that later, but from basic knowledge we know that Q divided by T, the charge flown through a conductor or its cross section within a unit time is called current. So the rate of flow of charge basically. So we can find the dimension of charge using this expression, current into time. And for current we use the basic fundamental dimension A, which you can say came from ampere, and for T we use time. For time we use T. Okay, so for charge the dimension is A T. Okay, so charge is not a fundamental quantity. Surprisingly, it is not. So you have to keep that in mind. Well, it doesn't really matter because the dimensional question, we are not going to target any question or any exam here, so it's just for knowledge. That's it. But we are going to understand it much further than normal, or rather say we are going to go on a considerably high level for this, for a student or junior student not in a college. Okay, so we can say that. I don't know, I don't really know how much level do they teach in other countries. I don't know really, so I can't say anything about it. We can just study if you want. If you don't like it, you can just leave, no problem. So that's it. Now, okay, we can see the next topic here, force between two charges. So now this might be new for some students. I know most of you know about this, but still it's more similar to what you expect to see in gravitation. If you have studied it, then very well. If you have not, then we may take gravitation classes after electrostatics, because electrostatics will help us a lot in gravitation, because they are exactly the same except for Kepler's law of planetary motion. So yeah, so we have two charges, q1 and q2. Write it. Okay, force, I'll write it. Force, I'll just write force. Okay, you'll understand if you have watched the lecture. Of course, this was the lecture. I would suggest you to, and if you can understand from the PDF, you can just save your time and just revise it. So we have to understand that this force is directly proportional to q1, directly proportional to q2, and this force is inversely proportional to the distance between these two charges. Okay, so this inverse relation is very similar to what we expect in Newton's law of gravitation. We find it from the inverse square law, which Sir Isaac Newton used to derive the expression for the gravitational law. But this is quite similar to that, and we will find an expression very similar to this called the Coulomb's expression, and the constant for gravitation is g, and for constant here what we get when we remove the proportionality is k, called the Coulomb's constant. Okay, let's begin. F is equal to q1 q2 divided by r square. I have already removed the proportionality constant and replace it with the equal mark. Now we will have to put a constant here called k, and this is very important. You might not want to confuse it with dielectrics, which we'll be studying later, but of course this is, for now you have to understand this is k. Okay, we will use another term from dielectrics. We can, these are just variables. We can't really change this constant variable. Okay, the k has a value called 1 by 4 pi epsilon naught, and here we find a new term, epsilon naught. Don't call it E naught. Okay, it's epsilon naught. So epsilon naught, this epsilon naught is called permittivity of free space. Permittivity of free space. This constant is the one determining that what we are calculating is all in a vacuum situation, or you may call that in air. So it's quite similar to vacuum, being in vacuum. Now it's quite similar to being in vacuum, but you have to understand that we will use dielectrics to alter this. This constant will change, and we will have different electric fields in different in different mediums. Okay, and you will find in very later chapters that this epsilon naught is related to our very favorite, very well known medium dependent quantity called refractive index. So this is very important. This is very I can't really This is very interesting. Okay, so that's it. This value is equal to this whole 1 by 4 pi epsilon naught k is equal to 9 into 10 to the power 9. Okay, let's go for the units. Newton meter per coulomb square. Okay, Newton meter per coulomb square. Now this Newton meter per coulomb square, but this epsilon naught can be found too, and you can easily do that by assuming the value of pi to be 3.14 and then interchanging or multiplying both sides by 4 pi and then taking the reciprocals. We can find the value of epsilon naught too. Okay, that would be 8.85 times 10 raised to the power minus 12. This is 8.85 divided by, okay, there is no division, sorry. This is unit is coulomb square plus divided by Newton meter. So you can see that this is exactly the reciprocal, so we have the units reversed. Okay, the dimension for K, if you want to remember that, you can easily find them from this unit, but I'll still tell you, ml cube t minus 4a minus 2. Here we have it, the force due to the due to charges. Okay, let's go to the next page. Okay, let's just hop on to the next property of charge. Okay, the smallest charge. This is something we need to discuss. What is the smallest charge that can exist? Okay, the smallest charge is called E, and this is exactly equal to the charge present, the magnitude of charge present on an electron or a proton. This is equal to the magnitude, I'll say the magnitude is equal to 1.6 into 10 raised to power minus 19 coulomb. This is the smallest charge you can find. Okay, there cannot be any small charge, and I'll tell you why it can't be divided. You might just say we can just break an electron and go into two pieces and the charge will just half. No, it doesn't work like that. Okay, there are a few charges smaller that we found in nature or in theories, but I think it's not safe to discuss on this level. I'll just tell you, there is a quantity, or you might say an entity, called quark. This quark is said to have charge of E by 3 or 2E by 3. Okay, quark. Now you might say, is the quark a third division or third part of an electron? Now we can't really say that, is it or is it not? I do not know about this much. I know quark has a smaller charge than electron, and we know all about it from the Big Bang, which is a theory proposing how the universe was made, and they say initially the quarks joined together to make the subatomic particles called electron, proton, neutron, and then they began to collide with each other, or you may say be in their each other's force due to nuclear forces, due to these electrostatic forces, and make an atom. So this is how it started. So we don't have to go much into it. I'll just tell you why. Just ignore it. Okay, I just told you for knowledge. This electron's charge is to be remembered, and this electron's charge is important. This is the smallest charge possible for us. Quantization of charge. This is a very important topic. Quantization. The charge is quantized. Okay. Q is equal to plus minus Ne. This is a very popular formula. You might have seen it before. This means that any charge is a multiple of E. This means the smallest charge possible cannot be divided, and we cannot get a value between E or 2E. We cannot get something like 3E by 2. You take, you getting me? Right. Only multiples. This is not possible. Only E, 2E, 3E, something like that is possible. Okay. You can't get 3 by 2 or 4 E by 3, something like that. These are still greater than E. These are not the smallest, not smaller than the smallest charge possible, but they cannot be an entity because they are not quantized. Charge is quantized. Okay. Now this is a very important topic we have now. Not very important, okay, of course this is not very important, but this is very interesting, I rather say. From Einstein's relativity theory, we know that mass, velocity, and even mass, length, and even time changes in different frame of references relative to what the ground level is seeing, okay, or some person moving at a speed is seeing. This happens when the speeds we are talking about are in the order of speed of light. So one of the formula I'll tell you, this is all the formulas are same, okay, these are not to be remembered, not very important for now, but these are a formula, v square by c square. Now in this formula you can replace mass by taking here m naught, the actual rest mass. Rest mass is when the body is at rest. This time which actually from the ground frame we get, and similar we can get length. Okay, so I'm just talking about time. Okay, now here when you see it, t will be equal to t naught at what condition? This below whatever it is stays 1. It has to be 1, and for it to be 1, this v square by c square has to be 0. This v square by c square has to be 0. It means that c, you know that 3 times 10 raised to power 8 meter per second. C is this. Okay, c squared is even bigger. 9 times 10 raised to power 8 times 2 is 16 meter per second. Okay, so this is a very big number. You can't really compare small speeds like 30 meter per second with this, and 30 meter per second is quite high speed also. So when you compare the speeds we walk in, or even an airplane, or even in satellite moving around the earth, these speeds are not anywhere near this speed. The square of these speeds is never near this speed. So this is, of course, this quantity, the numerator is very small, very small, and it means this whole fraction here approaches 0, and when it approaches 0, this whole denominator becomes 1, and t is equal to t naught, which we usually get. But when we talk about speeds anywhere near the speed of light, here is the real thing that comes. It is not 0. It is not 0, and the time changes. But why are we talking about this? Even mass changes, time is changing. There is something that does not change. If a body has charge, the charge shall never change. It is a statement, you can say. Charge is relativistically invariant. Okay, charge does not change due to relativity. Very important and very interesting. Now let's go to the second one, law of conservation of charge. I won't write this, you know this, I'll just write the heading. Conservation of charge means the charge initially was, if the system isn't altered, or you might say charge hasn't been transferred from the system out of the system, that means the system is isolated, then the charge is conserved. The charge will always remain conserved in the system. How many, doesn't matter how many elements are there in the system, the charge will remain conserved. It will just change from one position to another if it has to. Okay, so this is one of the topics. Now we are done with the properties of charge. Okay, I think this is one of the most basic things, and we had to make a lecture on these, and these are one of the most interesting parts. Now the parts will get a bit harder for some people, mathematically harder, or if they are mathematically good, you are all clear, all set. And if you are not, then need not to worry, we are here to help you, and your interest shall not be taken down just because you are not good at maths. Even I am not good at maths, so I can't really say anything about anyone about mathematics or something. Mathematics is something that is harder, more hard, of course harder when it comes to the pure subject mathematics. In physics, the mathematics is doable, and we have to basically understand what actually is happening, and then the mathematics what will take us to the answer automatically, and that would be easy, or you might say doable. Okay, the next topics are for next lecture. We will be making, I'll be trying to make lecture every day, every single day I'll be trying to make lectures. So the next topic for us will be vector form of Coulomb's law. Okay, important, but you can use basic vectors and the Coulomb law separately, and combine it would be much easier. I'll tell you how. Okay, and a few very important class. This chapter is long, and we will take a lot of time completing these chapters and completing the whole electromagnetism. So stay tuned with me. If you like my videos, or if you liked this video, this is of course the first video. If you like this video, you might give it a like, or you might wanna subscribe, and if you don't, can just wait for other videos. If you like them, then you can subscribe. It's all upon you. Thank you, and have a nice day. Of course, my English isn't that good, sorry. Thank you for watching this.